The Wolfram language has quite a diverse collection of functions for solving and manipulating equations both symbolically and numerically. A good place to start is with the solve function, which is primarily a symbolic equation solver. This shows solve computing solutions for a pair of equations. The first argument in solve is the list of equations, and the second argument is a list of variables. The result is a list of solutions, and each solution is a list of rules. There's also a function solve values that computes the same solutions but that returns just the values of the variables rather than lists of rules for applications where the rules are not needed. The equations in the first argument in solve can be given either as a list or using logical operations like logical and logical or. For example, this shows the same equations entered using logical and. Solve supports several methods of including constraints on solutions. One method is by including inequalities or other constraints with the equations, as in this example where the constraint that x be larger than 0 is entered by including the inequality x greater than 0, which causes solve to return only the solution for which x is bigger than 0. Constraints can also be specified using region expressions. For example, this input solves for variables x and y that satisfy the equation y equal x, and such that the coordinate xy falls on the unit circle. That input uses the element function to enter the constraint. The traditional mathematical notation for element uses a character that looks a bit like a Greek letter epsilon. The expression here specifies that xy is an element of the region defined by the unit circle. The element character can be entered by typing escape, ELEM, escape, or using backslash and an open square bracket, then the word element, which is the name of the character, and a closing square bracket. As already noted, the element character is similar to the Greek letter epsilon, but the Greek letter epsilon is a different character and will not work like the element character. A condition that the variable x must be a real number can be entered by including element x, reals in the equations. Without that condition, the equation in this example has 4 solutions, including 2 imaginary solutions. In mathematical terminology, reals is called a domain. The traditional notation for the real number domain is a stylized capital letter R that can be entered by typing escape, the word reals, and a second escape. There's a similar character called a double-struck capital R, but that too is a different character. With those notations, the constraint that x is a real number can also be entered as x followed by the element character followed by the reals character. The condition that x and any other parameters in the input must be real can also be entered by including reals or the reals character as the third argument in solve. In addition to reals, there are several other common domains. For example, this shows solve restricted to the domain integers, so the result shows only integer solutions for this equation. The traditional notation for domain integers is a character that looks like a double-struck capital letter Z, which can be entered using escape, INTS, escape. With that notation, that same solve input can also be entered like this. Solutions returned by solve are often given using special expressions like conditional expressions or inverse functions. For example, solving for the argument of an undefined function f gives a result in terms of the formal inverse of that function. Applying input form to that result shows the inverse function expression. Inverse function expressions provide a way to represent the inverses of unknown functions. The warning message from solve reflects the fact that inverse functions often are not single-valued. For example, the equation sine of x equals a half has an infinite number of solutions. For that equation, however, the solve function uses a conditional expression to represent that infinite set of solutions. The first argument in conditional expression is the solution, which here is given in terms of a parameter c1, and the second argument in conditional expression gives the condition for that solution to be correct. The condition here is that the parameter c1 must be an element of the domain integers, and since the number of integers is infinite, this result represents an infinite number of solutions. Here's a modification of that input that includes an inequality to limit the range of x. With that extra restriction, there's only one solution. Results using conditional expression come up in many situations. For example, the conditional expressions in this result indicate that the specified solution is correct only when the parameter b is greater than 0, which happens because this equation has real solutions only when b is greater than 0. Solutions for equations involving polynomials are often represented using root expressions. For example, the solutions for this equation are represented using root expressions. A root expression is simply a way of representing the roots of a polynomial. Here's another example where all of the coefficients are numbers, so the root expressions are numeric. The default display of a numeric root expression shows numerical approximations for each root, but the underlying root expressions are still exact and are not numerical approximations. The actual root expressions can be seen by applying input form to that result. Roots of polynomials can also often be represented using radicals. For example, the 2radicals function can be used to show that result in terms of radicals. Root expressions are usually more compact than radicals, however, and can be used in calculations much like radicals. For example, here is one of the root expressions from that previous example. The result can be used in calculations, such as in this inequality, or it's possible to compute high-precision numerical approximations for that expression, and so on. Solutions using radicals can be especially bulky for polynomials with symbolic coefficients. For example, the solution in terms of radicals for this quartic polynomial is several pages long. In situations like this, it is sometimes convenient to get a solution in terms of root expressions, which for this quartic equation can be obtained by including the quartics option set to false in the input. There's also a cubics option for specifying that the solutions to cubic polynomials be represented using root expressions rather than using radicals. For this special case of computing roots of a polynomial rather than using solve, there's a separate function called roots. For example, this shows roots giving the roots of a cubic polynomial. For comparison, here is the equivalent result from solve, which gives the roots in a different order, but the values are the same. Also, unlike solve, the result from roots is given as a logical combination of equations rather than using lists of rules. The result from roots can be converted to lists of rules using the 2rules function. 2rules actually returns a sequence expression, enclosing that sequence expression in a list, and using sort to change the order gives a result that is the same as the result from solve. The solve function is primarily intended for working with exact symbolic equations. If the input includes inexact numbers, as in this example, solve returns a correct solution, but in this example, it generates a warning message about the inexact number. Equations with inexact numbers can be solved using nsolve. The nsolve function works much like solve, except that nsolve does certain parts of the calculation numerically using inexact numbers. For example, this gives inexact approximations in the result even though the input is exact. For the equation in this example, which happens to be a polynomial equation in one variable, there is also a function nroots, which is the numerical counterpart of the roots function. Nroots also gives the solution as a logical combination of equations rather than using lists of rules. An unrelated function for solving equations and finding roots numerically is findRoot. For example, this shows findRoot computing one of the roots of that equation. Unlike solve and nsolve and roots and nroots, findRoot finds one solution at a time and uses numerical methods that typically require starting values for each variable. Variables and starting values are specified in the second argument of findRoot. The other roots in this example can be computed by giving other starting values in the input to findRoot. FindRoot can find solutions for systems of equations and for equations with more than one variable. For example, this shows FindRoot finding a solution for 2 equations and 2 variables. When there's more than one variable, the second argument in FindRoot is a list of lists giving the name and starting value for each variable. FindRoot can find solutions for equations that solve and nsolve are unable to handle. For example, FindRoot quickly gives a solution for this equation. Solve and nsolve are designed primarily for solving equations that can somehow be transformed into polynomial equations. The equation in this example is a transcendental equation that cannot be solved by those methods. There are separate functions for the important special case of systems of linear equations. The solve function can solve linear equations. For example, this shows solve giving a solution for a set of 3 linear equations. But although solve can solve this problem, it is almost always more efficient to treat a system of linear equations as a matrix equation and then compute the solution using matrix operations. For example, the linear equations in that solve input are equivalent to the matrix equation shown here, with the elements in the matrix taken from the coefficients in the equations, and the solution can then be computed using those coefficient matrices as the arguments in the linear solve function. In addition to basic functions like solve and roots, there are lots of other lower level functions that are used internally by solve or that are otherwise useful in working with equations. For example, this shows the eliminate function combining two equations to eliminate a variable and return a single equation. Another useful function is solve always, shown here applied to a single equation and two variables. Solve always finds values of parameters that make the equations valid for all values of the variables. In this example, the result gives the values of the parameters a, b, c, and d that make the equation valid for all values of x and y. The logical notion of an equation being valid for all values of the variables can alternatively be expressed using a function called for all. This for all expression, for example, represents the logical statement that the equation in the second argument in for all is true for all values of x and y. That logical statement can be converted into an equivalent set of equations using a function called reduce. For all is an example of a type of logical statement called a quantifier, and the operation of replacing quantifiers by other logical operations is called quantifier elimination. Quantifier elimination is done by the resolve function, as in this input, which gives the same result. Resolve is used by reduce and also by solve. Although there is some overlap between solve and reduce, the general purpose of reduce is to return a modified set of equations and conditions that has the same solutions as the original equations, rather than specifically to find solutions. For example, this result from reduce includes the condition that the parameter b is not equal to 0, since that condition is necessary for the result to be logically equivalent to the original equation. Unlike reduce, the solve function gives solutions that are valid for generic values of the parameters. For example, the result from solve for that same equation gives a result that does not include the condition on the parameter b, and that is valid only for generic values of the parameter. Here's another example where the result from reduce includes equations that give one variable in terms of another, which is again not something that solve would do. General information on solving equations, especially symbolic equations, can be found in the Wolfram documentation in the TechNote on manipulating equations and inequalities. For polynomial equations, there is this page on complex polynomial systems, which describes additional details on functions like solve and reduce and a variety of related functions, and includes a more advanced discussion about the low-level mathematics of working with polynomial equations. Information on systems of linear equations can be found in the section on solving linear systems in the general TechNote on linear algebra, and information on solving equations numerically, such as using FindRoot, can be found in the sections on equations in the general TechNote on numerical operations on functions.